Okay, so SpaceX's hot staging had this crazy flaw. A 20,000-pound steel ring was making pressure bombs on every flight. The engines fired super close together, blasting 30,000 degrees exhaust that could have wrecked the booster in a heartbeat. But get this, SpaceX didn't give up. They figured out something so smart that the old design looks ancient. How did they turn a possible disaster into a huge win? It changes everything about how rockets separate. So what was wrong with SpaceX's first hot staging system? It was an engineering nightmare that was happening right under their noses. During the early tests, SpaceX engineers were watching the data like, uh-oh. Every hot staging sequence was creating pressure bombs inside the interstage. The upper stage's 3 Raptor engines would fire inside a metal cage, with no way for the exhaust to escape. It was like lighting a blowtorch in your garage and closing the door. The superhot gas had to go somewhere. In Starship's case, it bounced around inside that space, making pressure waves that could have torn the booster apart. The numbers were insane. 3 Raptor engines making over 500,000 pounds of thrust. Exhaust temps hitting 6,000 degrees Fahrenheit, hot enough to vaporize steel. And all of this was happening just 4 inches above the dome. I mean, most rocket stages separate with hundreds of feet between them. Starship was trying to do it with less space than your phone's width. The team knew they were playing with fire, for real. And here's where it gets wild. That dome wasn't just heavy for no reason. Every pound of that 20,000-pound steel ring was there to keep it from blowing up. Without that reinforcement, the pressure spikes would crush the dome like a soda can. They ran simulations, and they all said the same thing. Anything lighter would fail big time. The hot staging ring weighed more than 3 Falcon 1 rockets. That's not just heavy, it's ridiculous for something that's supposed to make the rocket better. The irony was harsh. The system meant to boost payload by 10% was actually dragging it down. Every ton of steel they added was a ton they couldn't carry to orbit. SpaceX was in a paradox. Make it lighter and it breaks. Make it stronger and it fails. There had to be another way. The answer came during Flight 9 and it changed everything. SpaceX did something that seemed backwards. They blocked vent holes in the hot staging adapter. Why trap more pressure inside something already risky? The answer showed how smart SpaceX's engineers are. They weren't fighting the pressure, they were controlling it. By blocking vents, they could direct the exhaust flow. This made enough force to flip the 250-ton booster where they wanted it to go. No more random tumbling, complete control using trapped exhaust pressure. But this also showed how crazy the hot staging is. The pressure was so intense that it could throw a skyscraper-sized rocket around like a toy. They weren't just dealing with weight or heat, they were fighting the physics of explosions, and physics always wins if you don't change the game. That's when someone at SpaceX had an idea. Look at old Soviet rocket designs from the 60s, the N-1 moon rocket and R-7. The Soviet engineers faced a support problem, but without the extra weight. Their solution was simple. Use triangular lattice frameworks that spread out the loads and stayed light. But the Soviets didn't have to deal with hot staging. Their frameworks only had to handle structural loads, not rocket exhaust at point-blank range. This is where SpaceX's idea gets amazing. What if they could take the Soviet trusses and engineer them for hot staging? What if, instead of fighting the exhaust, they could give it escape routes while keeping it strong? The new design is so clever that it seems too simple to work. Gone is the 20,000-pound steel dome. Gone is the ring. Now, the whole hot staging system is part of the booster structure. The Lattice uses triangular struts connected to hard points on the booster. Each triangle lets exhaust escape. Instead of trapping pressure, the new design channels it away from important parts. The truly smart move is that those triangular vents aren't random. Each one is engineered to handle pressure loads and heat. The Lattice isn't just lighter, it's better at protecting the booster during separation. Manufacturing is easier too. Instead of forging steel domes, SpaceX can weld together triangular sections. Each strut is self-contained, meaning damaged parts can be replaced without destroying the whole system. The weight savings are crazy. The new design could be 60 to 70% lighter than the old one. That's possibly 6 tons of weight savings, enough for a satellite constellation. But weight savings were just the start. The new design led to changes that could change rocket control forever. While redesigning the hot staging system, SpaceX reduced the grid fins from 4 to 3. This seems nuts. 4 fins give symmetrical control, while 3 fins make things asymmetrical. But SpaceX's data showed that the 4th grid fin wasn't helping. The booster was already stable with 3 fins, and the 4th was just extra weight and harder to make. The new 3-fin setup also lets them mount the fins directly on the methane tank instead of inside the interstage. This helps with aerodynamics and reduces the number of structural connection points that could fail. A tripod is stable on any surface, while a 4-legged table wobbles. In the chaos of re-entry, 3 fins might give better control than 4. But the biggest change is with the Raptor engines. Current Starship uses 3 vacuum-optimized Raptor engines for hot staging. All 3 fire at the same time, making that blast of exhaust that caused problems. Future versions will have 6 vacuum Raptors. This makes an interesting chance. Instead of igniting all the engines at once, Starship could light just 2 during separation. These would be placed to avoid blasting exhaust directly onto grid fins. The others would ignite after the stages separate and the exhaust has room to spread. This staggered way reduces stress on the hot staging system and gives more precision. It also gives fault tolerance. With 6 engines, Starship can handle an engine failure during hot staging and still complete the mission with 3 engines. Any failure during separation could mean losing both the booster and the upper stage. But this raises a question. SpaceX used to block vents to control the booster's flip. That relied on the old ring to trap and direct exhaust. The new Lattice, with its vent paths, seems to remove that pressure. So how will they control direction during separation? Some engineers think they'll block the Lattice vents themselves, turning sections on and off to direct exhaust. Others think the 6-engine setup will give control through differential thrust timing. There's even talk about using the grid fins as exhaust deflectors. The answer could change spacecraft control beyond Starship. The techniques SpaceX develops here will affect every future rocket, from lunar landers to Mars vehicles. This isn't just about solving Starship's hot staging. It's about changing how we think about stage separation, weight, and control in rocket design. The old way was brute force. Build it strong enough to survive. SpaceX's new way is precision. Engineer exactly what you need, where you need it, with nothing extra. Every other rocket company is watching because they could change reusable launch vehicles. These changes could make the difference between affordable space access and space remaining for only the rich. The question is whether SpaceX's solution works and whether they've opened the door to new ways that will define the next space exploration. What happens next could determine whether humans become a spacefaring species or stay on Earth. So here we are. SpaceX took a system that was breaking and turned it into their secret weapon, from a 20,000-pound steel cage to a Lattice that weighs 70% less, from random tumbling to precision control. This story shows how innovation happens. It's about admitting when something's broken and reimagining it. Most companies would have just made the steel ring thicker. SpaceX looked at Soviet rockets and said, "What if we could do this better?" The ripple effects are spreading. Blue Origin, Rocket Lab, and NASA are studying these techniques because when you solve a physics problem the right way, everyone notices. We're watching the birth of technologies that will carry humans to Mars and beyond. Every change in spacecraft design brings us closer to becoming an interplanetary species. What's next? Will SpaceX's grid fin change how we control things? Could their staggered engine ignition work for lunar landers? The answers are being written on launch pads, and I can't wait to see what comes next. What do you think will be the next big thing in rocket design? Drop your thoughts below and let's talk about the future of space. Raptor 3 hook no heat shield revolution. Right now, SpaceX's Raptor 3 is running without a heat shield. It's like driving a car without brakes. But it works. How is this possible? Every rocket engine needs protection from heat, but Elon's team just removed it. When fuel leaks in Raptor 3, it burns off like it's supposed to be there. NASA engineers are shocked. This engine now makes 280 tons of thrust while weighing 36% less than before. Even experts thought the first photos looked broken until SpaceX fired it up. So what's the secret? The engineering crisis that started it all. Traditional rocket engines are controlled bombs surrounded by a metal jacket, a heat shield. SpaceX engineers were facing a problem. The Raptor 2 needed over 10 tons of fire equipment to keep it from melting. That's like bringing a fire truck to deliver a pizza. With 33 engines on the super heavy booster.